Hello students, today's video is on inverse Trigo. Today I am going to discuss different types of important questions which were even asked in previous year's entrance exams. Please watch this video till end because I have covered the whole topic in one video. So this first question was asked in 2019 as well as 2013. So cot sigma n is from 1 to 19, cot inverse of 1 plus sigma p is from 1 to n, 2p and whole bracket. We have to find the value. Now in this case, I'm just rewriting this. I can write this as cot sigma n is from 1 to 19, cot inverse 1 plus, if I take 2 common from here, and using this formula that sigma p is from 1 to n, p is what sum of first and natural number, and that is n into n plus 1 upon 2. So if I use this formula here, I get cot sigma n is from 1 to 19, cot inverse of 1 plus 2 into n plus 1 upon 2. So now this comes out to be cot sigma n is from 1 to 19, and this is cot inverse of 1 plus n into n plus 1. Now further I can replace this cot by tan because it is easier to do it by the formula of tan. So I just replace it by the reciprocal further I can rewrite this as cot sigma n is from 1 to 19, and I can replace this numerator by n plus 1 minus n, which is 1. After solving we get 1 here. Now this is what, using the identity, and that identity is tan inverse of x minus tan inverse of y is tan inverse of x minus y upon 1 plus xy. So if I use this identity here, so this comes out to be cot sigma n is from 1 to 19, tan inverse of n plus 1 minus tan inverse of n. And if I open this summation, so what I get, this is equal to cot, if I put n equal to 1, I get tan inverse of 2 minus tan inverse of 1. Putting n equal to 2, I get tan inverse of 3 minus tan inverse of 2, and so on. Last, if I put n equal to 19, so this comes out to be tan inverse of 20 minus tan inverse of 19. So all the terms get cancelled out with each other, and we are left with only the last term, that is tan inverse of 20, and the first term, that is tan inverse of 1. So what we get here cot tan inverse of 20 minus tan inverse of 1. Further, I can replace this by using this identity that tan inverse of x plus cot inverse of x is equal to pi by 2. So I can replace tan inverse of x by pi by 2 minus cot inverse of x. So using this I can replace this tan inverse of 20 by pi by 2 minus cot inverse of 20 and tan inverse of 1 by pi by 2 minus cot inverse of 1. Further, this is equal to cot pi by 2 cancel out with pi by 2 and we are left with only cot inverse of 1 minus cot inverse of 20. And we reduce it into tan. So this is equal to tan inverse of 1 and minus tan inverse of its reciprocal, that is 1 by 20. Again, using the identity tan inverse of x minus tan inverse of y, we can replace this by tan inverse of x minus y upon 1 plus x into y. On further solving, I get this as tan inverse of 20 minus 1 upon 20 plus 1. That is tan inverse of 19 upon 21. And after reciprocating it, I get this comes out to be cot inverse of 21 by 19, and using the identity that cot inverse of x is x, so this comes out to be 21 upon 19. So my desired option is here, option B. So this is how we prove this type of question. For the another application of this type is, here we have to find sigma r is from 1 to n tan inverse of 2 to the power r minus 1 upon 1 plus 2 to the power 2r minus 1. I can rewrite this, and from denominator I can conclude, I can rewrite this denominator as 1 plus 2 to the power r into 2 to the power r minus 1. That is, if the bases are same, we can add the powers. So now I have to just change the numerator in the terms of these two terms. So I can rewrite this numerator as because this is going to be turned out into this type of formula, that is tan inverse of x minus tan inverse of y, and that is tan inverse of x minus y upon 1 plus x into y. The denominator is just similar to 1 plus x into y. I have to replace numerator as x minus y, and I can rewrite this numerator as 2 to the power r minus 2 to the power r minus 1. That is the difference of these two terms. We can check here, because if I replace numerator by this, so we can check that this is correct. If I take 2 to the power r minus 1 common from these two terms, so what I get 2 common here and minus 1 here, and this turned out to be 2 to the power r minus 1. That means just this. So that means I have reduced into correct form. Now, further, using the identity, this above identity, that is this, I can replace it by sigma r is from 1 to n tan inverse of 2 to the power r minus tan inverse of 2 to the power r minus 1. Now if I put r is from 1 to n, so by putting r equal to 1, I get tan inverse of 2 minus tan inverse of 1 sigma, therefore put plus sign here. If I put r equal to 2 here, I get tan inverse of 2 square minus tan inverse of 2 to the power 1, that is tan inverse of 2, and hence so on. After putting r equal to n, I get tan inverse of 2 to the power n minus tan inverse of 2 to the power n minus 1. And here all the terms get cancelled out with each other, and we are left with only first and last term. So here we are left with only tan inverse of 2 to the power 2n, that means this term, this is the last, and the first term. This is tan inverse of 1. And you know that tan inverse of 1 is is equal to pi by 4. So this is tan inverse of 2 to the power n minus pi by 4. So my desired option is here, B part. Now next type is, you have to find the value of x here. So that means, in this case, we just solve it. You have to find the value of x in one of the 4 options. Cos inverse of 2 by 3x plus cos inverse of 3 upon 4x is equal to pi by 2. And using the identity, that is cos inverse of x plus cos inverse of y is cos inverse of x into y minus root of 1 minus x square root of 1 minus y square. Using this identity, this comes out to be cos inverse of 2 upon 3x into 3 by 4x minus root of 1 minus 4 upon 9x square root of 1 minus 9 upon 16x square is equal to pi by 2. If I take this cos inverse to right hand side, what we get, this comes out to be 6 upon 12x square, and here after taking LCM, this is 9x square minus 4 upon 9x square, 16x square minus 9 upon 16x square is equal to cos of pi by 2, and cos pi by 2 is 0. Further solving, I get 6 on 12x square, and here I get 3x and 4x, that is 12x square is my LCM, so I can just write this as 6 minus root of 9x square minus 4 into 16x square minus 9 upon 12 of x square. And if I take to this side, this comes out to be 9x square minus 4, 16x square minus 9, and further on taking this term to right hand side, I get 6 is equal to 9x square minus 4, 16x square minus 9 on squaring. This comes out to be 36 9x square minus 4 into 16x square minus 9. Further solving, this is 36 is equal to 144 to the x to the power 4 minus 81x square minus 64x square and plus of 36. These two gets cancelled out with each other, and we are left with 144x to the power 4 minus 145x square, taking x square common, 144x square minus 145 equal to 0. On further solving, I get x square is equal to 0, implies x equal to 0, and from here 144 x square is equal to 145, x square is equal to root of 145 plus minus upon 12. It's only x. That means my x is equal to plus root 145 by 12 is the answer, because in my question it is given that x should be greater than 3 by 4. So my correct answer, my correct option is root of 145 by 12, as I get this as my answer. Where is my answer? X is equal to, rest we have to neglect these two values, x equal to 0 and x equal to minus root 145 by 12. So I get the correct option as option C. Another application is here. In this particular question, we have to remember few of Pythagorean triplets, and those are we are frequently using these 5 Pythagorean triples. Few of them are 3, 4, 5, 5, 12, 13, 7, 24, 25, 6, 8, 10, 8, 15, 17. These are very common Pythagorean triplet. 33, 56, 65, 20, 21, 29, 20, 99, 101, 17, 144, 140. These are very common Pythagorean triplets. Now, in my question, sine inverse 12 by 13 minus sine inverse of 3 by 5. And as we all know, the formula for tan is very simple. That is the tan of difference, that is tan inverse of x minus tan inverse of y, is simpler than tan inverse sine inverse of x minus sine inverse of y. Because tan inverse of x minus tan inverse of y is tan inverse of x minus y upon 1 plus xy. So we reduce these two tan. So using Pythagorean triplet, if my perpendicular is 12 and hypotenuse is 13, so my base would be 5 here. And similarly, this is my perpendicular and this is hypotenuse. So my base would be here 4. So I just use these Pythagorean triplet and I replace it by tan. Tan is perpendicular upon base. So this sine inverse of 12 by 13 is equal to tan inverse of 12 by 5. Similarly, sine inverse of 3 by 5 is equal to tan inverse of 3 by 4. And using the above identity, I can replace this by tan inverse of 12 by 5 minus 3 by 4 upon 1 plus 12 by 5 into 3 by 4. Further solving, I get this as tan inverse of 48 minus 15 upon 20, 20 plus 36 upon 20. On further solving, I get this is tan inverse of 33 upon 56. But my question is in terms of pi minus sine inverse of pi minus sine inverse of 63 by 65, pi by 2 minus sine inverse of 56 by pi by 2 minus cos inverse of 9 by 65, pi minus cos inverse of 33 by. So from here I conclude that if this is equal to tan inverse of 33 by 56, so in terms of cos, this is cos inverse of, and this is again a Pythagorean triplet, this one. So if my perpendicular is 33 and base is 56, so my hypotenuse would be 65. So I replace it by base upon hypotenuse, and further by checking the option I can replace, or using this identity, that sine inverse of x plus cos inverse of x is equal to pi by 2. So cos inverse of x is pi by 2 minus sine inverse of x. So I can replace this by pi by 2 minus sine inverse of 56 by 65, and that is my option, right? That is my option B. So this is how we solve this question. Now my next question is, this question is sine inverse of x by 5 plus cosec inverse of 5 by 4 is equal to pi by 2. Sine inverse of x by 5, if I take this to right hand side, so I can write this as pi by 2 minus cosec inverse of 5 by 4. Further, this can be replaced by sine because cosec is the reciprocal of sine. So I can rewrite this as pi by 2 minus sine inverse of 4 by 5. And here on LHS I have x by 5. Further, using this identity, that is sine inverse of x plus cos inverse of x is equal to pi by 2. So pi by 2 minus sine inverse of x is cos inverse of x. So using this, I can replace this by sine inverse of x by 5 is equal to cos inverse of 4 by 5. And using my Pythagorean triplet, this sine inverse of x by 5, and using this Python 3, 4, 5, if this is based upon hypotenuse, then my perpendicular would be 3. So if I use this Pythagorean triplet, this comes out to be sine inverse of 3 by 5. Further, I can write this as x by 5 is equal to 3 by 5. And further solving, what I get, x equal to 3 is my option, and x equal to 3 is the answer, and my correct option is the D option here. Now, next question is, know that the sum of infinite GP is A upon 1 minus R, where mod of R is less than 1. And in this particular question, which was asked in 2001, sine inverse x minus x square by 2 plus x cube by 4 minus and so on, plus cos inverse of x square minus x4 by 2 plus x to the power 6 by 4 minus and so on till infinity. So these terms are forming infinite GP, where in this case my first term is x and my common ratio is minus x by 2. This is again infinite GP with first term as x square and common ratio as minus of x square by 2. Using the formula of sum of infinite GP, this comes out to be x upon 1 plus x by 2. And this is cos inverse of x square upon 1 plus x square by 2 and is equal to pi by 2 given to us. And using this identity, that is cos inverse of x or sine inverse of x plus cos inverse of x is equal to pi by 2. Similarly, this is x and this is x. If I use this identity, in that case x should be equal on both the sides. X should be equal, so that means these two values are same. So I write this as equal to x square upon 1 plus, using this identity, 1 plus x square upon 2. Further taking LCM, I get 2x upon 2 plus x, and here 2x square upon 2 plus x square. 2x into 2 plus x square, 2x square into 2 plus x. On further solving, this comes out to be 4x plus 2x cube, 2x, 4x square plus 2x cube. On further solving, I get 4x square minus 4x equal to 0. 4x if I take common, so here I get x equal to 0 and x equal to 1. But it's given to us that this mod of x in the question is given to us that mod of x is in between 0 to root 2. So that means this is the given condition. So we cannot take x equal to 0 here. So my desired answer is x equal to 1, and my correct option is option B. The next question is, you should know that a sequence with repeating term, a sequence with repeating terms is both AP as well as GP. That means if I have 2, 2, 2, 2, 2 and so on, term 2 is repeating, then this is AP with common difference 0, and this is GP with common ratio 1. So a sequence with repeating terms is both AP as well as GP. In my question, X, Y, Z are in AP given to us, so that means 2y is equal to x plus z is my given condition. Next, tan inverse of x plus tan inverse of x, tan inverse of y, and tan inverse of z are also in AP. So that means we can write this that twice of tan inverse of y is equal to tan inverse of x plus tan inverse of z. And on further solving, by using the identities, one is that 2 tan inverse of x in terms of tan, because my question is in terms of tan inverse, so this we use 2 tan inverse of x as tan inverse of 2x upon 1 minus x square using this identity in LHS. And in RHS, I use tan inverse of x plus tan inverse of y is equal to tan inverse of x plus y upon 1 minus xy in my RHS. So this I use in RHS, this I use in LHS. So what I get here, if I use so my LHS comes out to be tan inverse of 2y upon 1 minus y square, because my LHS is 2 tan inverse of y, and my RHS turned out to be tan inverse of x plus z upon 1 minus x into z. And further I can write this, that 2y upon 1 minus y square is equal to x plus z upon 1 minus x into z. Using 1, that is 2y is equal to, using 1, that is 2y is equal to x plus z. I can replace this numerator of LHS by x plus z upon 1 minus y square, x plus z upon 1 minus x. On further solving, this gets cancelled out, and what we get, that y square is equal to xz, and this means that x, y, z are in GP. And my given condition was x, y, z are in AP, and I get x, y, z are in GP. That means if x, y, z are in both AP as well as GP, then in that case x is equal to y is equal to z is my answer. So my desired option is option A. Now, another application is here. This came in 2015. We know that tan 3 theta is 3 tan theta minus tan cube theta upon 1 minus 3 tan square theta. And in terms of inverse, this is 3 tan inverse of x is equal to tan inverse of 3x minus x cube upon 1 minus 3x square, provided this mod of x should be less than 1 by root 3, or 3x square should be less than 1, or x square should be less than 1 by 3, and further on solving I get this as my answer. So this is my given condition here. Now tan inverse of y is equal to tan inverse of x plus tan inverse of 2x upon 1 minus x square. Using the identity that 2 tan inverse of x is tan inverse of 2x upon 1 minus x square, I can replace this by tan inverse of x plus 2 times tan inverse of x using this. Further, this can be written as 2 plus 1, 3 tan inverse of x. And using my identity, this, I can replace this by tan inverse of y is equal to tan inverse of 3x minus x cube upon 1 minus 3x square. Further, what I get, y is equal to 3x minus x cube upon 1 minus 3x square. So my desired answer is So answer correct option is here C part. That is 3x minus x cube upon 1 minus 3x square. So y is this. So here are few important formulae of inverse Trigo. You can have a screenshot. I have few more formulae here. So you can get a screenshot here. I hope this video will help you to understand the topic. So please like and share it with people around you and subscribe my channel Method Wise. Thank you.